So we have our last module in Unit 8. Just a reminder, Unit 8 is one of your core quizzes, so make sure to really spend a lot of time here. The rest of the semester, all of the rest of the modules are just different types of hypothesis tests. So really getting down 20 and 21. 20 is the introduction, 21 is some quick final topics. Will really prepare you really well. For those of you going for certain grades, the later material is less required, right? You might not be taking a quiz on that. You still have to maintain those homework percentages overall, which means you probably have to do most of that, but just kind of keep that in mind. No matter what, this unit, 19, 20, 21, which is Unit 8, is kind of your last big core quiz. Oh, sorry, there we go. Okay, so let's get started. Sorry if my AC is a little loud. I don't know if I can edit this or anything. So we are making one small change to the setup, the hypotheses. So earlier we said, and sorry that this is kind of blurry, I guess our picture we included here could be better. So we're going to be using the normal curve to calculate our p-values. Module 17 and some of the pictures we've seen implied we were going to do that simulation method. The simulation method is totally viable and actually becoming more popular. But day to day, like what is StatCrunch programmed to do? StatCrunch is its own dedicated software. If you ask for something like it in Excel or other statistical software also, how would you do that there? It's based on the normal model and similar models. We'll learn one more in the class, or we'll learn a few more in the class, one very similar one. So that's going to change a little bit of our picture. It's still the sample value, so this is still a sample value, which is right now p hat. And if it's below the mean, you're going to shade further below. If it's above, further above. But previously we had two options for the alternative, that you're testing less than some specific given number or greater than. And now we're just going to give the option in what's called a two-tailed test, in testing that it's different. And a real sample value is only larger or smaller than the proposed null hypothesis value, but this indicates that we didn't come into the problem knowing which one, and that we're going to show that uncertainty by essentially doubling our p-value. So that's kind of the final outcome here. Okay, so how does this look like in practice? There are different surveys that go out to students. So there's this one here, apparently launched in 2001. So in the 2016 version, lots of students surveyed. Half said, so 50%, right? Said that they often or very often prepared 2 or more drafts of a paper or assignment before turning it in. So maybe you prepared a draft of your data project before turning it in. So are those results similar? Just a reminder, pretend that said Crafton. Are the results similar here at Crafton? And so let's say, this is a professor or a department who cares about drafts and writing. You do a little bit of writing in my class, I could care about that. I might not know if I expect you all to do more or less drafts than nationwide. Maybe for some reason we're better writers. And does that mean we do less drafts? I don't know. I'm a bad writer. I need lots of drafts and outline and rough drafts and then final drafts. I don't know. So I'm not even sure how that works. But let's just say, because of that, I don't know. I just want to figure out if we're different here. So before you might have noticed, how do I know to expect if it's less, more? You can just test that it's different. and it essentially doubles your p-value. You're going to get one actual sample value that's above or below the mean, what you're testing against, but we're going to imagine it could have been as far away on the other side, and that's how we represent the uncertainty of not knowing ahead of time which way we were testing. Okay, so we do our survey. 56% said that they often or very often. So Crafton students, 56% said they often or very often prepared 2 or more drafts. So more than, I believe, was it nationwide? Nationwide. All right, how different is that 56%? It came from 200 students, so it's a medium-sized sample. Okay, so we need to verify the conditions, calculate the p-value, and I don't know if we've calculated a p-value yet, so I think we'll go through some of that example here. We were given p-values in the introduction, module 20. Okay, so verify the conditions. So we need to make sure it's random. Somebody said it's random, so okay. The main condition is calculating the size of how the sample relates to the answers. So our p is 50%, and our sample size is 200. And so what are all our values here? Our sample size is 200, our p is 50%, and our p hat is 56%. You could use either p or p hat in the computation here. If you have p, it's a little better. P hat is fine. Most of the time you should get the same answer. You'd have to have like wildly different scenarios, which is probably unlikely. Okay, so n 200, p 0.5, so that's 100. N times 1 minus p, that one was half, so this is just going to be another half. It's again 200 times 0.5. These are both larger than 10, so we're good to go. Again, the verifying is just calculating that. Right, what are the mean and standard deviation of the distribution of sample proportions? Right, so for module 17, that sampling proportion idea, the mean is just going to be p, 50%. And the standard deviation is the standard error, and so that's the square root. Unlike in confidence intervals, this time we have p. Most of the time in confidence intervals you don't. Sometimes you could have a previous estimate, but this time we have p, so 0.5, 1 minus 0.5 divided by 200. .035. 3 decimal places is probably good enough. Okay, so you can see these were those answers already. Mean, standard deviation. So one way to get the p-values on your own, we're using the normal distribution to get the p-values, is to pull up StatCrunch. You could also calculate a z-score here, and then use the calculator built into Canvas. That's up to you. If you open up StatCrunch, you'll have this one. I still am going to recommend that you learn StatCrunch for actual confidence intervals and hypothesis testing, and I'll have a separate video just recapping how to do that for some of these same examples. Okay, so what is the p-value? So the p-value is this red area here. 56% was our sample value, p hat. And so this area is about 4%, 0.04. But these are the new setups. Sorry, I was trying to find it. Where our null hypothesis is this new not equal to, which is called the two-tailed test. And so that one needs to double the individual size of an area. If you use StatCrunch, the full version, not this one, the full hypothesis testing confidence interval menu screen, it knows it for you. So there's a big advantage there. So the real p-value is twice this size. It's like it includes an imaginary tail over there. And so twice that size will be 0.086 roughly. So 8.6%. This one's kind of weird because the tail size individually is small enough to reject. It's less. It would be less than 5%, right? This 4% is less than the 5%. But when we double, it's now larger. So that's definitely possible. That can happen quite a bit. And so we have to decide if it made more sense. Did we really know ahead of time that we expected Crafton students to have more drafts, or to have a draft more frequently, technically? Okay, so this is, in general, this is the p-value is too large. So the technical answer that I'm least interested in, this is fail to reject the null hypothesis. Our results are not statistically significant. But context is more important, so we do not have enough evidence to show Crafton students prepare more drafts. Prepare drafts at a, sorry, it wasn't more. Got to count myself there. We were trying to prove that it was just different. So we should really clarify here that it's different at a different percentage than nationwide. So 56 was different than 50. Any number was going to be different if it wasn't 50. It was larger. Was it different enough? In this case, no. We're not sure that Crafton students are different. So you can see a lot of times if you have an idea if it was going to be more or less, that's probably more common to set it up to calculate the p-value, but it could be good to do this to represent your uncertainty. Okay, similar scenario here, I believe. Same survey, 13.5% that they often or very often come to class without completing readings or assignments. So do you do your readings and homework essentially before class? So we gave it to 500 students. Let's see. That was given to nationwide students. Are this results similar at community colleges in California? I wonder why we're testing that. So let's see. We test California community college students, 10.5%. We tested 500. So less. So do we want to test less or do we want to test different? Those are both options. We would never test greater here because the results are not greater. Okay, so you can take a guess by what we just learned. We're going to test that they are different. So state the hypotheses. You're going to have to be able to do this on your own for at least 1 or 2 questions on a quiz. So just make sure you're able to also do this even if it's not multiple choice. There's a lot of little pieces here. The null and alternative hypothesis. What is that hypothesis? That's why it's a colon. That something about the population proportion. Your null is always equal. Right, you get 2 different percentages to compare. There's a 5% sitting in that wording, right? But that's the level of significance. That's not an actual proportion for coming to class unprepared. So it's 13.5% is P. The 10.5% is P hat. And so we were asked to compare that it's different. Once we know what the number is for P, the population proportion, then we fill that in, right? These have the same number, and we're asked to test that it's different. So you'll see on StatCrunch, it makes it pretty nice. It has this as a fill-in spot, and this, but it automatically fills everything else in because that's the structure of one. So that's really good to remind you. That's why I like using it more than these quick calculators here. Right, verify, so that's n times p, and n times 1 minus p. So 500 times p is 0.135, I just wrote it down. So 67.5, which is bigger than 10. I'm going to be lazy but smart here. 1 minus p, if p is only 13.5%, 1 minus that's going to be much larger. So this other one is going to be much larger than 10. So we'll be good on the other one. We don't really need to calculate it. Okay, so the mean, p, agrees with our setup. And again, that actually comes from the assumptions of the test. We assume the null hypothesis to be true. So this whole problem is assuming that we're sampling from a population that's 13.5%. And then we're going to check what are the chances that we see 10.5% or more. I think that could be very difficult to internalize, so just try your best. But when we went and described what is a p-value really, we talked about that very clearly, and that's what all of Module 17 was really trying to talk about. I know I referenced 17 a lot, because that was a big, bulky module, and that's where the technical aspect is here. Day-to-day, you're okay if that is a little fuzzy still. What you really need to focus on is one specific page in your notes. If you didn't make it to the end of the Module 20 video, that's page 210, that tells you, okay, what do you do with the p-value? That's more important than really specifically knowing what a p-value is. So the top of page 210, those two paragraphs, most important page in your notes. Okay, it's somewhere on Canvas, but day to day I'm used to the notes more than what specific place it is on Canvas. Okay, so you can see this was p hat, this was p. If we were to calculate, this one would have been the square root one. That's already there. I'm going to be lazy. That's plugged in. All right, so the sample is less, so that's why it's shaded to the left. But we wanted a not equal to test, a two-tailed test. Sorry, I don't know why I scrolled. It's right here. We wanted a two-tailed test. So we need to double that value there. So the p-value, 0.02275 times 2, so 0.046, 4.6%. I believe we were told 5% significance level. So 4.6 is less. So what do we do when our p-value is less? Again, you do have to set them up, get the p-values on your own also, at least once in the quiz, but the conclusion is a little more important. So what is the conclusion here? We reject the null hypothesis. I'm going to do this in my notes. You can choose if you want to do it in yours. So our original idea is what we assume to be true. And we've just decided that's wrong. You're a jury. Assume the person was innocent. You fairly considered all the evidence and said, no, there's no way. I no longer believe this person is innocent. That means you must accept the alternative. So now we're thinking the alternative. That's why there's some wording, reject the null hypothesis in favor of the alternative. Okay, so the results are statistically significant. Maybe you should write them out and just being lazy here. But what does that mean? So we have enough evidence to show that this was California this time, California students have a different percent from 13% that come unprepared. Okay, so that is kind of might be one of the more difficult pieces of the problem. What do we really do with that number? The rest might be a little more formulaic. Okay, so I want to highlight, I don't think it comes together too much in the notes. What do we actually do with this information? So, are California students different in how many come prepared to class? The answer is yes. Well, we only said that they're different. We probably want to be able to say that it's less, but even more importantly, we want to be able to say, well, what is that number then? So we learned confidence intervals first, but in reality, hypothesis tests often go first to show that there's some difference, it's more, it's less, there's a change. And then a confidence interval comes next to answer what exactly is it. So p-values are extremely popular through actual research, and so are confidence intervals. But one way to think about how to use them directly is to prove that there's a change and then explain what that new value is going to be and actually estimate it. Now, if you plug it into a confidence interval, you can estimate it. So it's kind of we learned them in maybe the opposite way that you might normally use them. And that's because hypothesis testing is harder, so we want to do confidence intervals first. It's one of the reasons why we did it first. Okay, so I'm going to leave this here. I don't think I'm going to add this one. There's a few examples, but they're very similar. I'll have a separate video, and what I'm going to do there is show you how to use StatCrunch to get to this result. But this menu title tells you where it is. So that finishes Unit 8, and however you want to calculate it, totally up to you. If you find an online calculator you like better than StatCrunch, feel free to use that. Old school TI-84s work well. Just make sure you know how to use it. And definitely you will need one on the test, so you either need Canvas open, StatCrunch open, your other software you found, your calculator. You do need something because you can't do these purely by hand because you don't know you can't find that shaded area of the normal curve on your own. So you actually need some advanced software. So that finishes Unit 8, the core of this course. It's only the core because it's the one we chose to focus on for hypothesis testing or inference in general. So you still have inference for means coming up in Unit 9, and two short things at the end, 10 and 11, they're each only one module that are slightly more advanced types of hypothesis tests. There are tons of hypothesis tests out there. I'm not a day-to-day practicing statistician. I wasn't a statistics major, and my master's is not in statistics. So there's even more out there that I'm definitely not familiar with, but they depend on the setup of your data. So we chose proportions first, and we're going to do means next, so we're switching to quantitative data, but I'm calling this the core because this is the one I want you to focus on for the kind of core mastery quiz. All right, I'll see you in Unit 9.